Hello and welcome to Power System Analysis 2. We are in this module 3.2. Okay. Now in this module 3.2, we will be seeing one of the examples of the cost, the optimization of the cost function. Okay. Before that, in the last class I slipped one slide. I just want to see that. It is that we have talked about this coordination equation, where that coordination equation is that the incremental cost should be, in order for an optimal operation, the incremental cost of all generators should be equal to lambda, that is the Lagrangian multiplier. Then only you will have an optimal operation. This coordination equation you need to keep in mind. This is called the coordination equation. Now I'll just give you one brief paragraph from the book. It says that the optimal loading of the generator corresponds to the equal incremental cost point of all generators. That is, this dC by dP should be same for all generators. Okay, this is called the coordination equation, and numbering K's are solved simultaneously with the load demand equation. Now, what is the load demand equation? The load demand equation is this summation of PGI minus PD equal to 0. Okay. To yield a solution of a Lagrange multiplier lambda at optimal loading of K generators. Okay, so we'll be talking about this illustration in this class. Now in this section, just below it, there is a simple algorithm in order to find the Lagrangian when you are using the Lagrangian in a computer. So what we do is that we choose a trial value of lambda. Okay, so with the trial value of lambda, we'll place IC values because the incremental cost at optimal point should be same. So we keep this incremental cost value as equal to lambda. We are here again for the iteration part. We need to understand that we cannot directly solve it. So we are doing an iteration that we say that the problem is that when we have a set of generators with different cost function, different C functions, okay, cost functions. Now we want to optimize it. Now we have learned that in order for the optimal state, all the incremental costs should be same and would be the value of lambda. Now we say that, okay, let us say that at one instance all the incremental costs are same, okay, and that should be some lambda. Now we assume a lambda and we say that, okay, lambda equal to this, let's say 50, 100 is the present value of lambda. At this value the optimal operation is carried out. Okay, we start from this assumption. So we get the value of lambda as 100, we place ICs to be 100. Now from the IC we solve the generation power generation. So if that is the IC values, then at what power will be the IC values that we get from the graph itself. Okay, the graph of, I'll show the graph. So this graph, okay, so this is only the C versus power. We can also plot IC versus power. Okay, so we say that IC at this IC, this would be the value of lambda. So we calculate the power. Now if now we need to understand that power should the summation of that power that we have found out with a assumed lambda, most of the time or all of the time it is not right, it will be something different. So how do you know that it is different? When we add all the powers, that power should be equal to PD, or the demand. If it's not equal to PD, then my lambda is wrong. The assumed lambda is wrong. So you cannot get exactly 0. So we take, okay, if it is not 0, if it is very close to 0, a very small number, you can say, okay, my lambda is somewhat correct. If my lambda is not correct and the value, the difference of the sum of all generating power and minus the demand is not same, then I have to change the value of lambda. So you will take, okay, 100 is not working, let us take 101. Now see, no, it is not working again. So we, but what we see that, okay, if I put 101, that sigma of PGI minus PD, it is increasing. No, we will not take that. We'll reduce. Let's say, let us take 95 now. Okay. Now see. Okay. Now it is reducing. Okay. Then we slowly we go on assuming different values of lambda, as long as when this equation matches, or even if they do not match, at least we can say that it matches to a very small value. We cannot get an exact value where the sigma PGI equal to PD, but at least sigma PGI minus PD equal to some epsilon, that's some small value that is acceptable for us. Okay, so with this we'll start for the example that the book talked about. Now in this example, the two generators are given, very interesting one. These two generators have two different ICs. The two different ICs are given by this equation. The generator 1 has this IC that is a function of only the real power generated by generator 1, and the second IC is only function of real power generated by the second one. So the question that the book says that assume that both units are operating at all time. Assume that they are operating at all time, and the total load varies from 40 megawatt to 250 megawatt. So the load that is supplied by the generator, sometime it is 40 to 250, maybe 40 for during the night and 250 maybe during the day. Okay, and the maximum and minimum load of each unit are to be 125 and 20. That means both of the unit, they can maximum they can produce 125 and minimum they can produce 20. You cannot get anything apart from these, okay, or anything outside this zone. So the generation should be between 20 and 125 respectively. How will the load be shared between the two units, or as the system load varies over a full range? That means now if the load varies from 40 to 250 megawatt, how will the sharing of the loads will be, considering the incremental cost? Okay. Now we start with the light load. What about light load? 40. So now the load, remember the load is assumed to be running from 40 to 250. Okay, and both generators are to work. We cannot stop one of them, to allow both of them to work. Now what happens is that when it is 40, okay, so at light load, that is 40, unit 1 has higher incremental fuel cost. How do you know that higher incremental fuel cost? You can see that the rate of fuel cost is more for generator 1. The constant 40 is more. Okay, so we cannot, for our 40 load, we cannot allow the generator 1 to run more than the minimum it can do, that is 20 megawatt. So the generator 1 will operate at 20 megawatt, for which the incremental cost would be 44 per megawatt hour. Now if the generator 1 is using 20, the generator 2 also will have to output 20, because the total should be equal to 40. Now if we use 20 for generator 2, the incremental cost comes to be 35. Okay, the incremental cost now comes to be 35. Thus, with an increase of the plant output, the additional load should be borne by unit 2 until the incremental cost comes equal to 44 per megawatt hour. Why 44 per megawatt hour? See, understand this. The two units are running together. Okay, now if we are talking about the minimum load is 40. Now we see running generator 1 is more costly. So running generator 1 is costly because the incremental cost is costly. So if we run more with let's say generator 1 takes 30 megawatt, it will be more costlier than the running generator 2. So we say, okay, generator 1 we will use you for the minimum what you can produce. You can produce a minimum of 20. So we keep you at 20. Now if we keep you at 20, my incremental cost will come as 44. Now the unit 2 will take the other part of the load, that is 20. Okay, now after that, when the unit 2 is taking 20, the incremental cost is 35. Unit 1 is 44, unit 2 is 35. Now that means, and now as slowly the load increases, I am not going to increase the load of unit 1. All the load will be bared by unit 2. Okay, till what point? Till the point unit 1 and unit 2 has the same incremental cost of 44. So until this point is reached, the incremental fuel cost of the plant corresponds to unit 2 alone. When the plant load is 40 megawatt, each unit operates at its minimum bound, 20 megawatt, and lambda is rupees 35 per megawatt. Okay, so again, until this point is reached, that is the 44 megawatt point is reached, the incremental fuel cost of the plant corresponds to that of unit 2 alone, because unit 1 I am not increasing. So till 44 megawatt is reached, 44 megawatt per hour is reached, I am not considering unit 1. Unit 1 will be there. All the extra increment of cost is taken by the unit 2. Okay, so when the load is 40 megawatt, each unit operates at its minimum bound, that is 20 megawatt, and the plant lambda is 35 per megawatt hour. Now what happens when the incremental cost runs to 44? We can see, we calculate the PG2, we can see the PG2 is providing 56 megawatt. So the total output is then 56 plus 20 is 76 megawatt. So until the point of 44 megawatt, now at the point of 44 megawatt, what happens? Unit 1 still is producing 20 megawatt. I am not increasing the output of unit 1. Unit 2, I am increased the output. So the unit 2, previously it was supplying 20 megawatt. Now when it is slowly the load is increased, the unit 2 also increases, and at the point of 44 megawatt, rupees 44 per megawatt hour, it is providing 56 watt. That means now the load is 56 plus 56 from the unit 2 and 20 from unit 1 equal to 76 megawatt. From this point onwards, the value of the plant load shared by the two units are found by assuming various values of lambda. Okay, now after this 44 megawatt, both unit 1 and unit 2 will work together. I mean, we are going to increase both unit 1 and both unit 2, but with a different value of lambda, such that the IC of the both of order of optimal operation, the IC should be same. Okay, so here is a table, okay, with have a different values of lambda. So you can see when the lambda is 35, unit 1 is producing 20, unit 2 is producing 20, total power is 40. Lambda is 44, unit 1 is producing 20, unit 2 is producing 56, and total power is 76. Lambda 50, the unit 1 will produce 50, unit 2 will produce 80, and you'll have 130. And so for the different values of lambda, okay, we have different outputs of the plants. So that so in the graph you can see the incremental fuel cost of one plant with the total plant output. Okay, now to find the load sharing between the units of the plant output, say 150 megawatt. So I ask you, at 150 megawatt, what is the load sharing? We find the curve from figure 7.3, that is the figure that is shown here, and corresponding plant lambda at is 52.22 per megawatt hour. The optimum, so you can see 150 megawatt, I need 150, so you go to the chart, I need 150 megawatt, then where should we see? We can see that with lambda 50 you have 130, with lambda 55 you have 175 as total power. So somewhere between 50 and 55 the lambda should be there in order to get an output of 150, and that value we'll get from the curve that is shown here. Okay, so you can see the output of both unit 1 and unit 2, and a particular value of lambda, okay, we should get that is the lambda of 52.2 per megawatt hour. So the optimal schedules of each unit of 150 plant can now be found out. So once you get the value of lambda, you can get the power of 2 units of Pg1 and Pg2, and you can see Pg1 plus Pg2 is equal to 150 megawatt. Okay, so this is the end of this class. We'll continue with one more example in the next class. Thank you.